Okay, so we are going to go ahead and continue on with the Unit 3 free response notes. So we are on question number 2. A machine is used to fill soda bottles in a factory. The bottles are labeled as containing 2 liters, but extra room at the top of the bottle allows for a maximum of 2.25 liters of soda before the bottle overflows. The standard deviation of the amount of soda put into the bottles by the machine is known to be 0.15 liter. Part A. Overfilling the bottle causes a mess on the assembly line, but consumers will complain if bottles contain less than 2 liters. If the machine is set to fill the bottles with an average of 2.08 liters, what proportion of bottles will be overfilled? Okay, so we can figure out this proportion by using our normal model. Okay, so I'm going to go ahead and find the associated z-score. Now, going back to the original problem, I know that the mean, right, the average amount that is put into a bottle is mu, and then we know from up here that our standard deviation is 0.15 liters. Okay, so that's going to be important to us. Now we're going to go ahead and write down that z-score formula. Okay, so z is equal to x minus the mu, the mean over standard deviation. Right, so then we have a normal model. I'm going to write it down. Our mean is 2.08 and standard deviation is 0.15. Alright, now we have all the pieces. We know that we want to see how much, what percentage of the bottles is going to be overflowing, and so we know that 2.25 liters is when it starts to overflow, and so that's going to be our x in this case. Now let's just go ahead and define what x is. So let x equal the amount of soda put into the bottle. Okay, now the question is saying what proportion of bottles will be overfilled, and so we're finding the probability that x is going to be greater than 2.25 liters, because that's when it starts to overflow. Okay, so the probability that x is greater than 2.25 liters. Now I'm going to go ahead and start finding that probability by finding my z-score. Okay, so z-score is equal to 2.25 minus 2.08 over 0.15. Okay, so that's our when it starts to overflow, there's our mean, and then there's our standard deviation. When you punch that into the calculator, you're going to get 1.13. Okay. Now, once you have that z-score, you can go to your table to find the area. Now, just thinking about what we have. So ultimately, the probability that we want to find, right, is going to match the area that's above 2.25 liters. Okay, so this is what we want. And we just found the z-score for this value, 2.25, so it's 1.13. Okay, the thing is, though, when we look at the table, the area below the table is going to be less, and so that means that I'm going to go ahead and take the complement of that, so 1 minus the probability that x is less than 2.25. Okay, so 1 minus, now let me go ahead and look for the actual area. So my z-score is 1.13, so going to the table, here is 1.1, and here is 3. So 1.13, 0.8708, 0.8708. Okay, then I'm going to go ahead and subtract that. So we have 1 minus 0.8708, and we got 0.1292. And so that's going to be 12.92%. Okay, so the question asks what proportion of bottles will be overfilled. So I'm going to say 12.92% of the bottles will be overfilled. Okay. Part B. If the management requires that no more than 3% of the bottles should be overfilled, the machine should be set to fill the bottles with what mean amount? Okay, so now we're interested in finding out what the mean is, and we want to make sure that no more than 3% are going to be overfilled. Okay, and so let's think about what that means. So no more than 3% will be overfilled. So let's just draw a picture so that we could try to solve for this problem. So I'm over here. So being overfilled is at 2.25 liters. Okay, so I want this part to be 0.03, which means that the area that's below, which is 0.97, is going to be the percentage of bottles that are not overfilled. Okay, now everything in our table is based off percentage below, and so I'm going to go ahead and use the 97% in this scenario, right? So 97% is below. So let me write out what that probability looks like. So we want to force that the probability of a bottle having less than 2.25 liters in it to be 97%. Okay, and so what I'm going to do this time is I'm going to go ahead and go to my Z table and look for 0.9700, the one that's closest to it, and look at its associated Z-score. So 0.9700, 19, okay, 0.9699, that's only 0.0001 away. Okay, so I'm going to use that one, and the Z-score of that, so I'm going to go back to the table, so that's 1.88. Okay, so my Z-score is 1.88. Okay, now what I'm going to do, I'm going to think about my formula. So Z is equal to our observation minus mu over the standard deviation. Okay, now our observation is 2.25 because that's how much you can have before it starts to go over. And then we're looking for the mean. We have standard deviation, and then we just found the Z-score. So now this is just an algebra problem. So I'm going to go ahead and substitute everything in. So I have 1.88 is equal to 2.25 minus mu over the standard deviation, which is 0.15. And now we just have algebra. Okay, so I'm going to go ahead and multiply 0.15 on both sides. Right, so 1.88 times 0.15, we get 0.282 is equal to 2.25 minus the mean. Okay, now I'm going to go ahead and I'm going to just subtract that over. So 2.82 minus 2.25, and we have negative 1.968 is equal to negative mu. And so our mean is going to be 1.968 liters. Okay, and now I'm going to make sure I have my units now because we are talking about the mean. Okay, so Z-scores have no units. When you have the probability or percentage, the unit is the percentage, and then for mean and standard deviation, you want to start putting the units. Okay, now part C. Complaints from consumer about underfilled bottles leads the company to set the mean amount to 2.15 liters. Okay, in this situation, what standard deviation would allow for no more than 3% of the bottles to be overfilled? Right, so it's a very similar problem to what we did above. Alright, so we now have a new mean though, and this time we are looking for standard deviation. That's what we don't know. Okay, so the probability that the bottles are going to be less than 2.25 liters filled is still 97%, 0.97, and so that z-score isn't going to change, so we have 1.88. Okay, and so I'm going to go ahead and plug everything in, and so z is equal to the observation minus mean over the standard deviation, so my z-score is 1.88. The observation for you to get overfilled is 2.25. Our new mean is 2.15, and then now we're looking for standard deviation. Okay, so I'm going to go ahead and get rid of that fraction, so multiply standard deviation on both sides, and this is what we get. And then I'm going to go ahead and divide by 1.88 to get this by itself. And we're going to get that the standard deviation is going to be 0.053 liters after punching that into the calculator. Okay, and again, I made sure that I had my units. Okay, now that is the solutions for this question 2. We're going to go ahead and take a look at question 3. So question 3 comes from 2014. It is question 3, but I only included part A because that's all we know how to do right now. We will see the problem again once we learn the other content, but the question is testing. So I'm going to go ahead and flip this over. So number 3. Schools in a certain state receive funding based on the number of students who attend school. To determine the number of students who attend school, one school day is selected at random, and the number of students in attendance that day is counted and used for funding purposes. The daily number of absences at high school A in the state is approximately normally distributed with a mean of 120 students and a standard deviation of 10.5 students. So part A. If more than 140 students are absent on the day of the attendance count, if more than 140 students are absent on the day the attendance count is taken for funding purposes, the school will lose some of its state funding in the subsequent year. Approximately, what is the probability that high school A will lose some state funding? Okay, so we do have a normal distribution. It told us that the mean was 120 and the standard deviation was 10.5. Okay, so we have a normal model with a mean of 120 and the standard deviation of 10.5. So ultimately, we want to figure out the probability that we will lose funding. So if more than 140 students, right? So if more than 140 students are absent, right, that's when we're going to lose funding. So this is ultimately the probability that we are going to find. Now we have this x, right? So I'm going to go ahead and take the time to actually define what that means to us. So let x be the number of students absent. Okay, so we want to start actually explicitly defining our variables on the actual problem. So when I read this, the probability that the number of students absent is more than 40 is equal to, right? So if we define that variable, now I can read this out loud. Okay, so this is the probability that we're looking for. So if I were just going to draw this on a normal model, right? Our mean is 120, so 140 is somewhere above the mean. I want to find ultimately that area. Okay, now we're going to do the same thing that we've been doing. So we want to go ahead and find the z-score so that we can actually use our z-table. So z is equal to x minus the mean over the standard deviation. So z is equal to, so 140 is our parameter of interest. The mean is 120, and our standard deviation is 10.5. Oops, realize I put 10.15 up here for some reason, so it's 10.5. Let me just fix that. Okay, so once I have this, I can calculate my z-score. When I do this, this is approximately going to be 1.9. Alright, now here's the thing that happens. So this, when I look at this at the table, it's going to find me that area that's below, and I want the area that's above, and so I'm going to have to take the complement. So ultimately, I'm going to have 1 minus the probability that x is less than 140. Okay. So now let me look for 1.9 on my z table. So 1.9, here's 1.90. So my area is 0.9713. So this is 0.91, let me look at this again, 9713. Okay, and then when I actually do that subtraction, I will get 0.0287. Okay, and so that is my final answer. And then if I wanted to write this out in a sentence, I would say that there is a 2.87% chance that high school A will lose some state funding. Okay, so there's that one. So let's go ahead and do the last one. Okay, so we have another question. This time, this one comes from 2009. This is question number 2. I'm only including part A because, again, we still don't know how to do the full problem, but we'll see this problem again. Okay, so a tire manufacturer designed a new thread pattern for its all-weather tires. Repeated tests were conducted on cars of approximately the same weight traveling at 60 miles per hour. The test showed that the new treat pattern enables the cars to stop completely in an average distance of 125 feet. There is my mean, with a standard deviation of 6.5 feet. And that the stopping distances are approximately normally distributed. Okay. So part A, what is the 70th percentile of the distribution of stopping distances? Okay, now percentile. So how this works, if I were going to draw out this normal model, okay, there's some value A, right? I'm just going to go ahead and call it A. If A is the 70th percentile, what I'm saying is that the area below A is 0.7, right? It's equal to 70%. So if you are the 70th percentile, you have 70% of the data below you, and then you have 30% of the data above you, okay? So this is what we're looking at. And so if I'm going to write this out using my notation, so I'm going to go ahead and say let x be the stopping distance. Okay, we have essentially with the information, we have that the probability that the stopping distance x is going to be less than some number a, which I don't know, that's going to be a 70% chance, right? Because that matches with the area. So we have 0.7. Okay, so what I'm going to do, I'm going to go ahead and find the z-score by going to my z table and looking for 0.70 in the area part. Okay, so 0.70. So I have this one being the closest, right? 0.6985. It's the closest because it's close. It's 0.0015 away versus this one. This is 0.0019 away. Okay, so the associated z-score with this value is 0.52. Okay, so my z-score is 0.52. Okay, now I'm going to go ahead and just do some algebra. Right, so we have a normal model, so let me explicitly write this out. So we have a normal model, its mean is 125, our standard deviation is 6.5. Okay, so I have my z-score, here's my z-score formula. Z is equal to the observation minus the mean over the standard deviation. Then we just plug in the stuff I know. So 0.52 is the z-score that's associated with being the 70th percentile, right? So 70% of the data below. X, the observation, that's what I'm trying to find. I'm trying to find that stopping distance, and so that's going to be that A that I wrote down here because I don't know it, minus the mean, which is the 125, over your standard deviation, which is 6.5. Okay. At this point, it is now just going to be algebra, so I'm going to go ahead and multiply 6.5 on both sides. So we have 0.52 times 6.5 is equal to A minus 125. Okay, and then we would add that 125 to both sides, so I have 0.52 times 6.5 plus 125. That's what's going to equal A. When you punch that into your calculator, we're going to get 128.4. Now here's the thing, so this is a number that we just calculated that has a units, okay? And all of this is in terms of feet, so I'm going to make sure that I put the units there. Okay, and that's it. So, make sure you study because you do have a free response coming up. If you have any questions, feel free to send me an email.